So much for having me and for recording these in general. I was telling Tibby yesterday that this is such a gift to the community, and it's like having a textbook of contemporary glaciology on YouTube. It's wonderful. One of the other things I've really appreciated about it was also getting to know my colleagues more as people as well. So I thought I'd start my talk talking a little bit about how I got into this area and ended up giving this talk. So I grew up outside of Cleveland, Ohio, and I spent most of my childhood helping my dad, who was an appliance repairman, fix and build things. I started off sort of as early as I could remember, holding flashlights while he worked, and then eventually handing him tools. And then eventually, when I was a teenager, it got to a spot where I would go and do the entire repair while he sat and drank coffee in somebody's kitchen. It was actually a lot like being a graduate student, I think. No one in my family had ever gone to college, and we certainly wouldn't have used these words at the time, but I think it was my first exposure to engineering, to designing and fabricating things, and to the scientific method. You know, while we were doing repairs, you'd have to come up with a hypothesis for why someone's microwave wasn't working, and then find a way to test that hypothesis. And as clear as that connection is to me now, it certainly wasn't at the time. And I didn't see much of a point in what I was learning in school. I didn't like school, and I did poorly at it. Fortunately, my mom basically forced me to try out for my school science Olympiad team. So, you know, I went and I tried out, and I instantly fell in love. I loved the engineering events, building and designing things. I loved being part of a team. And I went on to really love observational science and astronomy. So much so that I joined the Cleveland Astronomical Society, where I ended up meeting Dan Akrib, who is a professor at Case Western Reserve University in Cleveland, and who invited me to do research on dark matter with him for the summer. And I was super lucky that my parents were supportive when I told them that I wanted to quit my paying lifeguard job and go look for invisible particles that may or may not exist in an unpaid research gig, and that I was going to need their car so that I could drive into the city. And really luckily, my mom turned to my dad and was like, "You have a motorcycle, give him your car." And through that experience, I learned sort of what college was, what research was, that people, real people actually were paid to do science. And Science Olympiad had such a transformative impact on my life. I started doing well at school and got a scholarship to go to college, and have stayed involved since. In grad school, my wife and I coached a high school team in Austin, Texas, the LASA high school team. And I'm now the head of all Earth and space science events for the national organization. So if you ever find yourself wanting to get involved or more involved with Science Olympiad, please just let me know. As lucky as I was to find Science Olympiad, it's still unbelievable to me that I've ended up in a spot where I get to give this talk today. But I got to not only go to college, but do my PhD with Don Blankenship at the University of Texas and participate in the first 3 seasons of the IceCap project, that I got to host an IGS symposium at Stanford following the symposia that Paco and Prasad hosted in Madrid and Kansas, or that I got to edit an Annals of Glaciology volume. Like, I think if you run ensemble simulations of my life 10,000 times, I get to do anything like this in like 2 of them. But as surprising and wonderful as it is to me that this is my life, you know, many of the things that I love most about my job now are in common with what I loved about Science Olympiad. There's inventing and engineering things, there's observational science, and then there's leading a team that's competing in science and engineering. And I'm so lucky to advise some of the, you know, smartest, most wonderful people I've ever met. And I'm so grateful for this opportunity to share some of their work with you. In terms of background, this seminar series has so many great talks. You can watch Richard's talk or Helen Fricker's talk and get an idea of why, or countless others, of why it's important to understand the background of why glaciers and ice sheets and their subsurface conditions are critical for sea level rise and for fundamental science. So I'm just going to dive right in and talk to you about my favorite topic, which is the science and engineering of ice penetrating radar. Most ice penetrating radar data is collected from airplanes along profiles and then gridded up into bed maps that give us images of bed topography that can then be used in ice sheet modeling. It also produces these beautiful cross-sectional profiles where we can see through kilometers of ice. So many geophysical media you're lucky to get sort of tens of meters into the subsurface. The fact that we can just see with such high signal to noise ratio through kilometers of ice is really an embarrassment of geophysical riches. Yet in our subfield, a lot of the work still is in these two categories, sort of bed mapping and interpreting images of radiograms. My research group is dedicated to going beyond those two interpretations and trying to quantitatively analyze and collect ice penetrating radar data to explore subsurface processes. Every process and condition on this diagram is something my group is actively working on, observing, and understanding. My group's pretty evenly split between electrical engineering and geophysics, with my most engineering-focused students inventing new radar systems and signal processing approaches to observe the subsurface of ice sheets, and my most geophysically focused students focused on analyzing that data and interpreting how, at a fundamental level, ice sheets behave. And a big group of both work in the middle, sort of on signal processing and interpretation. To give you an idea of the sort of information we're talking about, you can look at this radiogram of a subglacial lake by Sasha Carter. You can see, one, it looks like a lake. It's flat next to some topography that clearly isn't. If you look at the reflectivity values in this table from Knut Christiansen, you can see that subglacial water reflects like 30 or 40 dB more strongly than the surrounding area. That's like 1,000 or 10,000 times stronger. That's a nice, bright signal that you could feel pretty good interpreting. But the same physics that makes that such a good signal, also, if you look at the plot from Kenny Matsuoka at the top, shows that you have variations in attenuation rate from a couple of dB per kilometer to like 50 dB per kilometer. So there's an inherent ambiguity whenever you have a variation in an echo, a subsurface echo in radar. And this is a lot of the challenge and also a lot of the fun in radioglaciology. So now I'm going to share some vignettes of my students working. Like so many talks, I'm going to start focusing on Thwaites. You can watch lots of talks about why Thwaites is so specifically and particularly important and such a focus of fieldwork right now. But I think there's also some questions we can only answer about Thwaites by looking at its neighbors, particularly its boundary with Pine Island. For example, the fact that ice flows from the Bentley Trench into Pine Island Glacier has always been weird to me. If you asked me to draw reasonable physical looking boundaries to two glacier catchments, I don't think I ever am inspired to add this lump to the edge of Pine Island Glacier. And if you do the type of subglacial water modeling that Christine Dow presented in her IGS seminar talk, you can see that the water flows from the Bentley Trench into Thwaites. This is also deeply weird to have water and ice flowing in opposite directions. I think one of the reasons that this area remains mysterious is it not only lies on the boundary of these two glaciers, it lies on the boundary of the UTIG and Bass surveys of each glacier respectively. Now, we've been lucky enough to collaborate with David Vaughn and Hugh Core at Bass and Don Blankenship and Duncan Young at Texas to combine and cross-calibrate these data sets. And we're excited to release these cross-catchment grids and the radargrams as soon as this paper makes it through review, which hopefully is very soon. This work's been led by Winnie Chu, who's a former postdoc from my group, who's now an assistant professor at Georgia Tech. I've been super lucky to work with Winnie throughout most of my career. She first came to work with me when she was a PhD student of Robin Bell's at Lamont and came to work at JPL with me. She then joined my group as an early postdoc and helped me build my group and mentor many of my students. And a lot of what I'll present today that my students are doing has really benefited from having Winnie in the group and as a collaborator. In this particular piece of work, what she did was she took advantage of these direct reflights by the PASN system from Bass and the HICAR system from UTIG, cross-calibrated the systems and was able to make this cross-catchment reflectivity map. And for the question at hand, what stands out is this area of low reflectivity right at the outlet of the Bentley Trench going into Thwaites, suggesting that the bed may be frozen there. And this is in contrast to Pine Island, where it's sort of thawed all the way up to that boundary. So it is possible that the reason ice flows into Pine Island is because of this frozen patch. And if this patch was to thaw, the ice might flow into Thwaites, causing Thwaites to capture that piece of the Pine Island catchment. If we look downstream, you hit the eastern shear margin of Thwaites, which is the boundary of the two glaciers. And ever since Joe McGregor's 2013 paper, I think it's been a provocative question why the eastern shear margin is where it is. If you look at all these other shear margin glacier black lines, they more or less follow bed topography. And even the eastern shear margin itself, crosses over high topography, does not follow that topography. Again, I wouldn't draw it there. But even my follow-on work which analyzed the radar across these catchments and showed that it was higher reflectivity, so maybe thawed or wet in the fast-flowing regions, leaves you with a sort of chicken and an egg situation. Is it bright and thawed because it's flowing fast, or is it flowing fast because it's thawed or wet? Fortunately, my group's part of the TIME project, which is one of the projects within the larger ITGCU, which people have talked about, and we've working with Slavik Tulicek and Paul Christofferson and others, specifically looking at the eastern shear margin of Thwaites. And in particular, the radar team's looking at two hypotheses that perhaps more subtle processes like internal temperature and crystal fabric are playing an important role in this shear margin's location and behavior. So my PhD student, Nicole Beinart, is looking at temperature as a hypothesis that could be controlling it. And what she's developed is a radar system which uses a PRES transmitter as a transmitter, and then a software-defined radio as a receiver that you can move farther and further away to allow you to do tomography across the margin and observe and constrain temperature anomalies. Now, in order to get really long offsets, many kilometers, Nicole had to overcome losses that traditional systems had. You know, a lot of GPRs are not synchronized, so you can't get coherent gain to be at big separations. If there are cables, there are cable losses. And she's even shown that we can use coupling to get beyond the total internal reflection angle. So all of these things together, the synchronization approach she's developed, allows us to have really long offsets. Also, we've sent Nicole's system to the field with collaborators before, so if this seems like something that would be useful to you, let us know and we may be able to loan you one. There's also a beautiful body of work by my former postdoc, Tom Jordan, who's a Marie Curie fellow, jointly supervised by Jonathan Bamber and myself, who's now at the Plymouth Marine Lab, showing that we can use polarimetric radar data to constrain crystal orientation fabric. And I think to appreciate the elegance of Tom's work, if you look at those bottom plots, those are analytic calculations. And if you look at the top ones, that's field data. And the fact that those patterns match so closely shows that you can actually do a lot if you have polarimetric data to constrain fabric, which is not only below the resolution of the radar, but is below the wavelength of the radar. Now, a lot of our radar systems are not polarimetric. So luckily, TJ Young, who's a postdoc with Paul Christofferson at SPRI, but is a frequent visitor and honorary member of our group, looked at what you could do with single polarization data and was looking at birefringence fringes, basically noise in the data, and was able to, again, constrain, by adapting Tom's work, the fabric distribution and strength across the shear margin. So my hope for the TIME project is we'll leave with really detailed data and much more subtle techniques geophysically to understand this shear margin and apply that to others. Now, if you go further downstream, you hit the eastern shear margin, or eastern ice shelf of Thwaites. If you saw Aaron Pettit's talk, you can see why this ice shelf is so interesting and important, and why there's a whole separate field campaign focused on analyzing it. But for the purpose now, you can just see that it's an area of blue slowing ice in an area of otherwise red accelerating ice. The other unique thing about it is it's the location of one of the first, and I actually think might be the very first radar sounding measurement collected in the Amundsen Sea embayment. So you can see that orange line from 1979 is a SPRI survey line that crosses the eastern ice shelf of Thwaites and crosses two modern lines. Now, in order to use this data, we had to first scan the archival data, which was on optical film. So we were really lucky to partner and collaborate with Julian Dowdswell and the staff at SPRI to go and travel with two art historians and scan 1,000 canisters of archival film, corresponding like 400,000 line kilometers of data. You can see in those top two radargrams, our scan in the middle and a published print of the same piece of film, that this resulted in much higher fidelity scans of the data. And if you look at the eastern ice shelf, what you can see immediately, I mean, for me, the most striking thing is this top radargram. I'd be super proud if I was a radar engineer from the 60s and 70s of how favorable my radargrams look recorded on film with modern data below. But the other thing, you know, in Erin's talk, she talks a lot about the regrounding of the ice shelf on the offshore pinning point. And you can see in 1979 how much more regrounding there is on that pinning point. And you can see in 2009 the reduction. You can also see the non-uniform melt across the ice shelf. So I'm really excited to see the results from the Tarzan project. And hopefully this analysis and their measurements can be pieced together to give us like a 40-year image of how this ice shelf has evolved. Now, for me, the original motivation, or maybe the thing that I was most excited about, was not just to do geometric measurements of how things changed, but to do the sort of radiometric analysis that I do with modern data. Now, the archival film had Z-scopes, so you can see on the top, it looks like a radargram. However, to fit in the finite dynamic range of film, pretty exotic compression had to be used, and it was very hard to directly radiometrically analyze that. There were A-scopes, which are, basically photographs of oscilloscope traces. So that's real radiometric information, but they're infrequent. So the A-scope traces correspond to those red lines on the top. But fortunately, because again, these were such good engineers and kept really great notebooks, we have circuit diagrams and we have internal tests that we've been able to do to calibrate those Z-scope records, to use them radiometrically. And if you look at the bottom, this is a near reef light in East Antarctica. The left side, you can look at the radiograms first, right? The left side and the right side, that's film and modern data. You can see the shape of the floating piece of the ice shelf looks similar. But if you look below, also the reflectivity measures. So that left side, that's Z-scope film with an empirical correction for the radiometric signal, and then correcting for attenuation and producing these reflectivity patterns between modern data and the old data. And I think how similar these are. One, I don't know if it's coming across, but this is like one of the coolest things that I've ever been a part of. And the second thing is, hopefully this will motivate people to refly those original SPRI flights so that we can see areas where there's been more change. Now, as great as it was to produce like 2 million images of this film and then archive it in a permanent way with the Stanford libraries, it's a big lift to start using those scans. So one of the things I couldn't be prouder of is my students, students including summer students, undergrads, grad students, and postdocs work together to produce this open source, much more user-friendly tool to explore the data. So radarfilm.studio is now live. You can look after, or I guess during the talk, and start using the data. This is still in development, but we'd be thrilled if people started using and or contributing to this project. One of the exciting things about these surveys is actually that over much of the survey, there was simultaneous 360 megahertz data collected. So that's great. However, it is not labeled which is which on the film. So fortunately, Olivia Flournoy, one of the undergrads in our group, has been developing an automatic classifier system, and hopefully radarfilm.studio should have frequency information in the near future. Now, in addition to looking backwards and seeing how things have evolved, we're also interested in what will affect the ice sheets going forward. And if you watch Doug Ben's talk, you know that the thermal dynamics of the bed of the ice sheet can have a big impact on glacier behavior and dynamics. For me, one of the things that got me first thinking about the temperature of the bed was actually this area between Thwaites and Pine Island that in my own radar analysis showed that it was frozen, and Ian Yakin's modeling showed it was frozen. And I was interested in the specific question of what if this piece of the bed thawed, what would the impact be? My PhD student, Eliza Dawson, has a more nuanced and far-reaching perspective. She tends to think of the bed in 3 categories for this purpose. 1, an area of the bed that is thawed, so it's at the pressure melting point. 2, areas of the bed that are definitely frozen, way below the pressure melting point. And 3, thawable areas of the bed that are frozen, but are close enough to thawing that you could imagine something thawing them. So in Eliza's first paper, she's exploring this by doing some ISSM modeling in collaboration with Helen Sarosi and looking at what happens when we take these thawable regions and change their basal friction coefficient from the coefficients they have to the distribution of coefficients for thawed areas and seeing what impact that has. And in her second paper, she'll use radar sounding data to go beyond the simple dichotomy of sort of frozen versus thawed to look at these thawable regions and say, this piece of the bed right here, this is 1, 2, 5, 10 degrees below freezing. It's going to be so complicated and so much fun. If you saw Schroeder's talk, you know that subglacial geology can also play a significant role in how ice sheets evolve. If you saw Christina Hulba's talk, you know we can learn a lot about the contemporary bed of the ice sheet by looking at the deglaciated continental shelf. For example, we know that Paleo Pine Island ice stream retreated across an area of deformable sediments and then an area of outcropping bedrock. And we know that modeling studies of contemporary glaciers, if you just change the rheology associated with that geologic difference, it can be the difference between whether they retreat or remain stable. Now, the challenge that Schroeder highlighted is the complication and the logistic overhead to collect high fidelity geophysical information over a whole glacier catchment scale. So what we'd like is the ability to have that information, but at the scale required for ice sheet modeling. Now, fortunately, geostatistics is a technique that is built to provide that type of information. So my student, PhD student, Mickey Mackay's whole PhD thesis is focused on taking geostatistical approaches and adapting and expanding them to the subglacial environment. She has a paper with ensembles of ice sheet wide bed realizations that are geostatistically equivalent, and these complement and differ from maps like BedMap2 or Mashu-Morgan's bed machine collections. And Ricky has also shown that even between statistically equivalent realizations, you can have massive differences in where subglacial water gets routed. If you watch Jenny Catania's talk, you also know that geomorphologic detail of the bed can govern where and how far ice sheet outlets retreat. But for the problem at hand, what this enables us to do is to use pieces of high resolution marine bathymetry and marine geologic information on the deglaciated continental shelf as training data, apply that to these interpolated bed topography products, and then classify regions of the contemporary bed as more like the deformable sediments regions of the continental shelf or more like the outcropping bedrock regions of the continental shelf. And I think this is our best shot at present to take the type of fine geophysical constraints that Schroeder was talking about and produce gridded products at the scale that could allow you to do ice sheet modeling on them. Now, if you saw Michaela King's talk, you know that surface melt has an important and complicated impact on ice dynamics. And if you watched his talk last week, you know that my PhD student Riley Kohlberg was specifically looking at the impact of the 2012 extreme melt season. So by looking at UHF radar data, he was able to show not only that the ice layers from that extreme melt year were persistent years later, but by doing some sophisticated full wave simulation of the sub-resolution character of the ice layer and surrounding firn, he was able to show that in subsequent years, it persisted, that layer expanded in its conductivity, and that it got denser. This suggests that it's not just the single year of extreme melt that impacts the ice sheet. It actually, the frozen layers of those extreme years serve to precipitate a positive feedback in terms of impermeability, causing even in normal years that followed that ice layer to expand and densify. One of the most exciting opportunities for understanding this process is, to me, is actually at the confluence of 3 lines of work from our group. So the first is this elegant model data synthesis from Winnie. So in this study, what Winnie did was use ISSM to predict attenuation in Helheim Glacier, and then looked at the radar data and attributed any excess of attenuation to englacial water storage. And with this, she was able to pretty amazingly reproduce ground-based seismic observations of how much water there was in a firn aquifer. The second line of work is a collaboration with Nana Carlson and Jorgen Dahl to scan the archives at DTU of 1960s and 70s radar film of the Greenland ice sheet. If you would apply the type of radiometric calibrations I was working on that I talked about earlier to this data, and then apply Winnie's type of analysis, I think we have a sporting chance at looking at the quantitative difference between englacial water storage from the 60s and 70s to today. Now, we're not just interested in these processes going backwards, we're interested in looking at them as they happen in real time going forward. So our group's been very lucky to be collaborators on Paul Christofferson's Responder project on Store Glacier. And as part of that, Alex Kendrick, who is a PhD student at Stanford who did his second project in our group, looked at a deployment of a MIMO PRES array that was left out through the winter on Store Glacier. And what he saw is that you got weaker and weaker reflections from layers corresponding to attenuation of up to 50 dB. Again, this is 10 to the 5th. This is a monster signal, but it also is a signal you would expect if all of the local melt went into the ice sheet and then stayed there into the winter in glacially. So this both challenged our sort of naive initial mental model that in Greenland, you get big, beautiful lakes on the surface, they find a mullen somewhere, they drain to the bottom, and then you're done. And perhaps suggests that englacial storage explains some of the variation that Michaela was seeing in terms of response to meltwater input. This same collaboration gave us a surprise opportunity to also look at crevasse processes. So when the team went out in 2008, they deployed this beautiful linear array. And when they went back in 2009, a crevasse had opened directly underneath the array. So this offered a really exciting opportunity to try and see that crevasse forming in real time, because this is a time series deployment. So another undergrad student in our group, Kluva McLeod, who is a Girls on Ice alumna, and I would have loved to keep in glaciology, but to her credit and our loss, she'll be starting a PhD at the intersection of engineering and public policy this fall. But as part of this project, what she did, she looked at that data and was hoping to just see the crevasse open. But I mean, that radar arrays bend through a lot. So Ku's done a great body of work in correcting all sorts of artifacts that were introduced by the violence that was done to the system, but now has a really promising crevasse signature that I think we're going to be able to give constraints on the geometry and timing of its formation. So in addition to analyzing these measurements of ice sheets themselves, our group is also an engineering group, and we're also inventing new ways to observe things. So the first thing in that front you might ask is, well, why don't we just put one of these things on a satellite and observe them from orbit? After all, we do that at Mars. Now, one thing which you know of this talk is that attenuation is super temperature dependent, and it's warmer on Earth than it is at Mars. So the attenuation is higher. You need a higher power system. The clutter environment can also be more challenging. Martin Altenberg, one of our undergraduate students, is looking at crevasse clutter and trying to constrain that for geometries and frequencies of orbital sounding. And Riley did a piece of work that showed there's actually particular challenges associated with quasi-specular clutter from internal to firm. But I think more than that, there are challenges associated with Earth having a much stronger ionosphere than Mars, and there's the FCC and its international equivalents regulating what you can transmit, which you just, again, don't have at Mars. None of this is going to stop us from trying, but these are challenges that make it harder than it might appear. Another promising platform, if you can't do satellites, or you can't do satellites exactly as you'd like, is to use long duration drones. And one of the promising things about drones is they can actually adapt their surveys. And so, you can imagine that we don't just use profiles of ice thickness straight into even bed topography, right? So sometimes you want to take a survey where it's lots of adjacent repeat flights and process them to do high fidelity swath mapping of the bed, like this paper by Nick Holshoe, or other work by John Payton. You can also, do interpolation, like mass conservation by Matthew Morgan, or Mickey's geostatistical interpolation. And you can imagine that how you would collect the data in each of these cases would be different. And so one of the amazing things in using drones is you can adapt and have a patchwork of these styles of data acquisition for different pieces of the ice sheet that require different survey geometries. So what Thomas Theisberg, one of my PhD students' thesis is dedicated to, is to take advantage of the autonomy and adaptability of drone surveying to piece together and adaptively adjust these survey geometries and make promises like, for a given amount of fuel, data, cost, that you are reducing, say, the uncertainty in sea level due to uncertainty in bed topography, the most possible per unit resource. Now, in addition to surface and bed echoes, you can get a lot of information from in-glacial layers. For example, Elisa Mantelli, who is a former Stanford postdoc, who came to work with us after working with Christian Schoof and will be starting a faculty position at the University of Tasmania later this year, showed that if you can measure the slope of internal layers much more finely than you can in, say, a radargram as an image, you can place constraints on semi-temperate sliding in the onset of ice streams. Similarly, Cooper Ellsworth, who was another second project student who's now at the CART lab, showed that if you take an upstream radargram and create synthetic versions of it that are advected down through different flow histories and compare it to a downstream radargram, you can actually constrain pretty complicated flow histories using those profiles. Some of the most exciting work, I think, is taking these internal echoes and using them as a function of time. So Paul Summers, another second project student, is looking at what happens if you leave a PRES out long enough that it is advected significantly downstream, and is showing that you can get the difference in horizontal sliding velocities between the surface, the bed, and as a function of depth, which can give you insights into sliding mechanics. My former postdoc, Davide Castelletti, who's now at Capella Space, showed that if you can take reflights of airborne data and use internal layers, do interferometry with them to get vertical velocities. So just like we do INSAR of the surface to get horizontal velocities, you can get vertical velocities. And Thomas is picking this up and combining and expanding these types of vertical velocity constraints with surface velocities to try and then constrain the 3D ice flow of the ice sheet. If you saw Eric Grignot's seminar, where he talked about the transformative impact of surface INSAR, our hope would be that this 3D version of it would expand that impact further. And Thomas, I know, is in particular excited about the idea of feeding those velocities into machine learning approaches that can simultaneously solve for uncertainty in ice flow mechanics, basal sliding, bed topography, and the velocity sort of all at once. So we're not just working on inventing our own approaches, we also take advantage of amazing radars made by other people. So the ultra wideband system that's being flown by Croesus in Alabama and Avi had this provocative observation beneath Hiawatha Glacier in Greenland that seemed to be a groundwater table. And if you watch Bernd Kulessa and Louis Gustafsson's talk, you know that subglacial groundwater is both important and difficult to observe. Yet here we have this echo that seems to be groundwater. So one of our summer students, John Bissett, who is a visiting student from SUNY Buffalo and is now a PhD student in mechanical engineering at MIT, looked at this echo, both its relative strength with the bed and its variation as a function of depth, and showed that one, it does seem to be groundwater. Two, the layer between the bed and the water table, either because it's so lost, needs to be frozen or needs to be highly fractured and well drained, which you could imagine happening underneath a crater. But it needs to be one of these two cases. And the other reason that we may be seeing this and not seeing it elsewhere is actually this wideband system has such good side lobes that the echo from the basal interface itself gets below these returns faster. So it's possible if we fly this system elsewhere that we'll see groundwater elsewhere. Oh. Now, it turns out side lobes also answer another mystery in radar sounding. So one of our undergrads, Annabelle Conger, is doing an honors thesis on what appears to be lake bottom reflectors in the SPRI data. So they looked at these reflectors in our scans, and they do seem to be reflectors, but we don't tend to see them in modern data. And what Annabelle showed is the reason we don't see them in, say, these ultra wideband systems or other higher frequency systems is that the attenuation of the water is too high at these higher frequencies. And the reason we don't see them in HICARS, which is the same frequency and uses the same antennas, is that HICARS is operated in a chirp mode, which is almost always better. And the SPRI data was operated in a short pulse mode, but for this one particular case of the side lobes that let you see the bottom of the lake, it's actually better to have it in short pulse mode, and provocatively, raises the potential that maybe we should operate HICARS as a short pulse radar sometimes. In a similar vein, my former postdoc, Matt Siegfried, who came to work with us after doing a PhD with Helen Fricker and is now an assistant professor at the Colorado School of Mines, looked at why, with one exception, almost all of the lakes we see in altimetry, we don't see in radar, and almost all the lakes we see in radar, we don't see in altimetry. So what Matt showed here is actually that the echo returns from the bed of subglacial Lake Whillans are lower than the surrounding area, but like they drilled there and there's definitely a lake down there, there's water down there. So what Matt showed is actually the reason for this, which may be related to its active lakiness, is that you're actually getting water up into the ice column, and that water in the ice is both attenuating and scattering the energy. So you don't see the lake as brightly. Now, as fun as it is to solve these mysteries to detecting and interpreting signals, it'd be nice if sometimes we could just take a radar signal and map it directly to bed conditions. So if you watched Rebecca Schlegel's talk, you know that sometimes with seismic data, you can do that. So my PhD student, Anna Broom, is working on developing a system that will allow us to more directly constrain subglacial conditions. So she's developing a software-defined radio-based system. It's going to be polarimetric to fix those birefringence losses. It's going to be a hybrid radar radiometer to correct for some attenuation. And it's going to be sort of wildly multiband. And to give you an idea about what types of constraints and corrections this makes, think about just a jump in reflection. So if you look at the top right and we get a increased reflection at a single frequency, it could be that that's a difference in materials, water versus not. It could be it's a change in roughness, rough versus smooth. And if you look at the bottom left corner, the combinations of roughness and material properties that produce any given echo is pretty wide. What Anna has shown is if we go very wide in frequencies, and this is much wider, say, than a wideband system. If you have like 1 megahertz, 10 megahertz, 100 megahertz, 3 orders of magnitude, the overlap in what it could be is small. And if you implement this with the radiometric fidelity that normally people would use for a radiometer, the overlap gets very small. We can have much more confidence in our interpretations with a system like this. Now, as exciting as it is to look at orbital systems and drones and really heterodox geometries and implementations of radar systems, I do think there are some problems that will require us to have long-lived deployments of sensor networks in order to capture the processes as they happen. There's been some great preliminary work by Leib and Locke and Liz Bagshaw on systems that you do deploy and leave out. But I think in some cases, certainly in planetary cases, and in some of our more extreme cases, we really need to push the resource envelope super low. And so a promising approach on this front is passive radar sounding. My very first PhD student, Sean Peters, who's now at MIT Lincoln Labs and will be starting as an assistant professor at the Naval Postgraduate School this fall, did a whole thesis on passive radar sounding and showed that the approach, illustrated here for the sun, is that you digitize the entire electromagnetic environment, very similar to ambient noise seismic. And then you, instead of cross-correlating stations, you auto-correlate. And so if you have, say, the signal from the sun, it's random white noise that looks like nothing else, but it looks just like its own reflection. It looks just like itself. And when you autocorrelate that reflection, you're able to detect it. So Sean demonstrated this first in Big Sur using reflections from the ocean surface on a relatively wind-free day. That's sort of the easiest geophysical target, but it made us believe it would work. Then he deployed it in Death Valley, and we were able to do it off of the desert floor, but again, not going through ice. And then finally, in an opportunistic deployment, as part of our collaboration on Store Glacier, he was able to use some downtime and do a test on Store Glacier and get that reflection, which is in the bottom left there, which was really an echo from the bottom of the Greenland ice sheet from the sun through autocorrelation. So I think especially with Sean starting his position this fall and with the interest in planetary applications, I think this technique has, a long future, and I'm excited to keep working on it. So in addition to this body of work, our group also works on the science and engineering of ice penetrating radar for planetary exploration. I'm lucky to be a science team member on the Europa Clipper mission and on its radar sounder Reason, as well as a collaborator on RHIME, its sister radar on the JUICE mission. And everything I've talked about so far more or less applies to looking through the shells of icy moons, except rather than flying 100 meters over the surface with a 10 kilowatt transmitter, you're flying hundreds of kilometers over the surface with like a 10-watt transmitter. But as you know, attenuation is super temperature dependent, and space, thankfully, is very cold. So the first question we're trying to answer with Reason is the ice shell thick or thin? Is it like a couple meters thick, or is it tens of meters thick? And if you were to choose a frequency with which to sound an ice shell, you might choose to go really low in frequency so that when you hit a rough piece of the surface, your wavelengths are nice and long and aren't that affected by propagating through it. However, it's the case at Jupiter that particles from Io's volcanoes interact with the Jovian magnetic field and produce these really strong radio signals up to about 40 megahertz. So the approach we've taken with Reason is to have a two-band system, one at 9, which will perform better in rough areas, and one at 60, which will perform even when we get hit by this Jovian interference. Now, a question that people start to ask, and you may have asked at some point, it's tempting to ask about ice penetrating radars, is what is the penetration depth? This is an incredibly rude question. You should never ask it about a radar. And the reason is that the penetration depth is up to the target and not the radar, in large part, right? So if you look at that plot in the top right, this is a modeled ice shell for Europa. It's one of many models that could exist. But if we say, okay, well, what's its penetration depth? So let's say we have 100 dB to play with. You'd look at that black line, you'd look there and you say, okay, it gets red, I don't know, maybe 20 kilometers deep. You say, that's it, 20 kilometers, you can detect the ocean. You're not going deeper than that. What if it's 30 kilometers thick? So then you look at the right side of the plot and you can see you get down to like 28 kilometers, which is more than your 20 kilometers. And this makes sense. So, space is cold at the surface, the ocean is at the pressure melting point, and you don't really hit the attenuation until you get most of the way through. So that's good news, is that we'll get most of the way through most ice shells. Even better news is the second project by Jinsu Kula, another second project student who is looking at the eutectic point, so the point in the ice shell where salty ice would start to melt. Jinsu showed first that the attenuation down to the eutectic is even less, and then once you start to get melt and water at the eutectic, there are lots of ways to make that echo detectable to radar. So I think between mapping the attenuation and echoes from the eutectic, even if we don't see the ice-ocean interface everywhere, we're going to have strong geophysical constraints on the ice shell and its properties. Perhaps even better news is a growing body of work that suggests you can get liquid water in the shallow part of the ice shell. So work by Brittany Schmidt or my own postdoc, Gregor Steinbrugge, shows that there's reason to believe that Europa can have liquid water underneath chaos regions quite close to the surface or underneath impact craters that are associated with water plumes. And our hope would be that we get beautiful radargrams that look like this terrestrial radargram of an iceberg and you just see it. But Europa Clipper is a flyby mission. We're only going to have a handful of radargrams to look at. So before we declare there's a body of water and it might be habitable, we want to make sure that the echoes aren't coming from some pathological cliff off to the side that looks like it might be an echo from water. So in order to do this, Reason has a minimalistic two-channel system where you can do interferometry between the channels and tell there's an echo coming from nadir or off to the side. And another second project student, Roger Michaelides, who's now a postdoc with Matt at Mines, showed that in the long track direction, you can use the Doppler signatures of the echoes to distinguish between bottoms of floating blocks of water or crevasses or off-nadir scatter. I think as a whole, what I'd add is that icy moons are a really exciting way to both apply and refine our thinking as glaciologists in sort of more extreme environments. And I'd encourage everybody to think more about them. I'll close with saying how incredibly lucky I am that this is my job. I love everything about being a professor. I love teaching and mentoring students. I love the research we do. I love being of service to universities and to our community. But it is so unlikely that I would get to do this. In fact, this picture of a childhood costume that says Professor Dustin Schroeder is the only evidence I have that my parents or I knew what a professor was. And I was so lucky to have incredible mentors at critical points throughout my career. So in addition to the people in Cleveland who got me to go to college, when I got to college, Karen Morosi, the Assistant Dean of Engineering at Bucknell, was also a first-generation college student and helped me believe that I could afford to and attend and belonged at a place like Bucknell. And my own advisor in grad school, Don, was also a first-generation college student from the Midwest. And that helped me navigate a lot of things that would have been harder if it wasn't. I remember on my first international trip, I just like straight up maxed out my credit cards. I was checking out of a hotel and I just couldn't pay for it. And in an experience which would have been could have been very embarrassing and othering and class revealing, Don stepped in and paid for it and did the extra paperwork for the reimbursement and made it a teachable moment of learning about what a transition to a career in knowledge work that involved professional travel was like. Even after my PhD, other academics who were first generation or low income college students identified themselves in talks like this and responded to me when I reached out to them. And I've had other mentors who are underrepresented in academia along other axes or just in-group academics who are just wonderful advocates and mentors. So if you're watching this talk and have ever questioned like, is the professorate or academia or glaciology for people like me, either because you're also a first-gen low-income college student or because of the countless other reasons people have thoughts like that, don't hesitate to reach out to me. I have a karmic debt that I can never repay, so I'd be delighted to talk to you. And as would almost everyone in the community. I mean, I think that's one of the things I really love about the IGS is so many of the people on this call have taken time to talk to me and answer my numerous questions and share their perspective about this career. And I'm very grateful to you guys, and I miss seeing you all in person very much and hope we can do it again soon. I guess I'll close by saying that if you saw anything that interested in you in this talk, please feel encouraged to reach out to my graduate students. All of their emails are on my Group People website. And I'm sure after this year, they'd be delighted to talk about their work to anyone who isn't me. So with that, I'll say thank you for this wonderful opportunity, and please tune in next week for Drew's talk that I hope includes some radar, but I fear may not. Any questions? Stop sharing, maybe I can see the chat. So I see a chat to everyone from Frank. How does the basal temperature reconstruction of the Antarctic ice sheet inform the conditions of the selected oldest ice sites in the vicinity of LMC? Well, I certainly haven't analyzed that area myself in detail to give you a definitive answer on that. So I think this is one of the approaches we should use for it. What I will say on that front that is striking is in the modeling we've done at sort of the ice sheet wide scale, which initially for Eliza's work, we're just looking at the modeled basal temperatures and then doing these experiments with the basal friction coefficient. In the areas where I have done radar analysis like Thwaites or like some of the work on Institute Ice Stream, you can see with a lot of confidence that certain parameters or certain models from intercomparisons match the radar distributions really well and certain ones don't. So I do think there's potential, especially with the type of sort of model constraints that Winnie's been doing, to use the radar as a meaningful constraint on those conditions. So I think there's lots of reason for excitement in that line of work. I don't know if you guys are able to unmute yourself, but feel free to, or to raise your hand.
No, thank you, Dusty. It's a really informative. But it was a great talk, and it's really impressive to see not only your achievements, but also the huge group you have there and the variety of subjects that you're treating. So thanks a lot for this very nice talk.
Thanks, Frank. So it's like Doug's,
hey, Dusty,
Doug's hand.
This
Yeah.
is Doug. It turns out that you and I grew up in the same neighborhood, I think, because I also was a member of the Cleveland Astronomical Society, and that's sort of got me going in science as well. Just thought I'd add that.
Wow, that's great. I mean, I'll add to that also this mentor I had at Case who reached out, and I worked in his lab when he was also the undergraduate mentor to Kristen Poinar. So there seems to be something about Cleveland and astronomy that makes people not want to go into that field, but become glaciologists.
It was a great talk, Dusty. See you
Thanks.
later.
Hey, Dusty. Thanks for a great talk. It was really motivating. And also thanks to the IGS. I think this is a great opportunity for new PhD students who cannot even go to the conferences that we are all used to. So thank you very much. Dusty, if you were to bet on, I don't know, what initiates ice streams, is it anisotropy or is it basal hydrology? What do you think is more likely?
So I think I'm very biased by many conversations with my former postdoc, Elisa Mantelli. So I think she's totally convinced me that it's subtemperate sliding, which is the key to that. So I guess I would be loath to bet against her.
No, that's fine. Thank you. Yeah.
Dusty, do you have the next week's talk slide, or is that in
yeah, I was just doing
David's box there somewhere? Oh, that's right. Sorry, you already did it.
No, that's fine. I'm happy to share it. I just can't read the chat window when I do.
Okay. There's a question from Roger Clark there on the chat.
All right, well then I'll stop sharing.
Roger.
Okay, it says you have such wide coverage of the bed reflectivity of Pine Island Thwaites. Have you explored a wider set of seismic reflection correlations? No, I mean, so this paper has been one of the things my group's been working on the most, because my hope was that we would get this combined data set out to everyone so that everyone doing the ITGC measurements would have that as a 2004-2005 baseline. So our focus has really been on just getting that data as clean as we can, getting it as calibrated as we can, and then hopefully there'll be a whole body of work using that as a baseline, including hopefully seismic comparisons as well.
I've just been checking on the Facebook, and there's no questions there. There's mostly Tavi trying to explain her absence there. So, any more questions?
I could have one more. Dusty, this I forgot the name. The online archive where you make radar data available. Is this planned as a bigger thing so that other institutions maybe could also send their radar data? Because I think this would be a really great achievement to kind of consolidate all the things that we've collected over the last 40 years or so.
So I know, yeah, I'll put it in the chat.
Oh yeah,
so,
radar film. Yeah.
So what we've been focusing on is just the film. And I know there's a lot of other work. I know John Payton's working on trying to serve, all the different radar data. I think the film is its own sort of special challenge. And so I think for us, our hope, well, I mean, we just saw that even internally, it was such a lift to use this that we wanted to get it in a state that if somebody was a specialist on a particular glacier, they just wanted to get from, seeing if there were flight lines there to downloading the film to interpreting it in their study, that we wanted to lower that barrier of entry. And I think right now, so that's one thing. I think the other thing is the positioning was pre-GPS, and even the flights we have positioning for at all are relatively few. So there's pieces of work. I mean, it's beautiful for working with undergrads with, in that, sometimes you just have a flight number and it, the positioning stops, but, there's only so many places they flew from. It's only so long. And it's almost like doing a puzzle that you can put it into a spot. And so the infrastructure to have the community or have our own students put these puzzle pieces together to just figure where at all these things are is pretty different than something that you would use to analyze in a sophisticated way more contemporary data. So I think hopefully the project that John's trying to lead on the other front will be there, and maybe they'll merge in the end.
Okay, that sounds great. Thank you. Yeah.
Dusty, just a quick question. Since I was involved in radio echo sounding in Iceland in the 70s and 80s, do you know if there are other institutions that are doing something similar to their film records? I've never heard Helgi talk about it. So
when Helgi was here for the 2019 IGS symposium, we talked to him a lot about traveling to Iceland to scan that record as well, because a lot of the lift is sort of just getting this massive machine for digitizing it and then getting the expertise to sort of run it and deal with it. So our hope was, and our plans were pre-COVID, to actually, sort of summer 2020, go to Iceland and scan them. And so hopefully that will be possible again in the not too distant future. But yeah, that's one front. The other front that I've learned in some of our scans is, often we go there and scan the initial body, and then we find, people find a box of the film in the basement, and then they're a little more comfortable carrying it with them. So especially if people have smaller sets of film that's sort of hand carryable, then we can just bring it here and scan it. But we're certainly happy to help anybody who's got film.
Thank you. I'll chase after Helgi and see how he's doing.
It'd be great. Awesome. Well, thank you for taking time to see this. It was so great to sort of virtually see so many of you guys.
Okay, well, thank you very much, Dusty. It's absolutely fantastic. And do you have the power to shut things off now?
I think I may, so I'll try and do that.
Okay, well, great seeing you again, and thanks very much. Was a fantastic talk.
Thanks, Magnus. Great to see you.
Thank you.